Hello students, welcome to BTech first year physics course. In the last lecture, I have discussed about problems and solutions related to surface integral. And we have come across some important points and tricks for solving the surface integrals. Right? Now today, I shall discuss about volume integrals. Okay? So, what is volume integral? Suppose you consider a closed surface S in space and this encloses a volume V, and in this region if there exists a vector field A and a scalar field phi, then total volume integral or space integral of vector field A and scalar field phi can be written like this. Okay, and for example, total mass can be measured by the total volume integration of mass density, which is a scalar field, right? And total linear momentum is measured by total volume integration rho r Vr. Here rho is the mass density and V is the velocity of the mass. So this is the example of volume integral of vector field. Okay. Now to understand how one can perform volume integral, let's discuss few problems and their solutions. And you know, learning by doing is the best practice to understand any subject you read. Right? So let's start with first problem. Suppose we have a vector field F and the form is like this. Then we have to evaluate volume integral of the given vector field within the region bounded by the surfaces x equal to 0, y equal to 0, y equal to 6, z equal to x square and z equal to 4, which is shown in this figure. So here this is x equal to 0, this is y equal to 0 plane, this is y equal to 6 and this is z equal to x square, this curved surface, and the top one is z equal to 4. Okay. Now let's discuss different steps to understand the limits of the variables which are involved in the integration. As the volume integration involves integration of fields with respect to three variables x, y and z, here it is sometimes called triple integration. Okay. So as a result, in first step we will do the integration of the vector function with respect to z variable from z equal to x square to z equal to 4, from base here to top of the column PQ, and we have to keep x and y fixed. Next, in step 2, we have to integrate the function with respect to y variable from y equal to 0 to y equal to 6, from r here to s in this slab, keeping x fixed. Okay, and in last step we will do the integration with respect to x variable from x equal to 0 to x equal to 2. So how can we tell the upper limit is x equal to 2? Because where z equal to x square surface meets z equal to 4 plane, that corresponds to x equal to 2 point along x axis. So this is the curved surface z equal to x square that meets at z equal to 4 here along x axis, and that point correspond to x equal to 2. Okay. Now as we have all the limits for different variables, now we can use them for solving the integration. And as we have the vector function as the integrand, we have to divide it as component wise, and we get this form of volume integration. So first we have to solve this integration, right? So this is the ith component of the main volume integration, right? Now you see carefully. Here first we have to solve the sub integration with respect to z. Once you integrate, you will get the integrand which depends on x, because here in the lower limit we have x square, right? And we get this integration form. Now we can separate the sub integrations with respect to x and y and solve them, and we get this value. Then similarly for jth and kth components, if we proceed like that, then we get these integration values. And finally, if we add them, we get this final value of the volume integration. 128I minus 24J plus 384K. Okay. Now, let's discuss the next problem. Here, we have to evaluate the volume integration of a scalar function, which is 2x plus y. And volume here is the closed region bounded by the cylinder z equal to 4 minus x square and the planes x equal to 0, y equal to 0, y equal to 2 and z equal to 0 planes, which is in this region, right? Now, to do the volume integration of the scalar function, first we have to integrate it with respect to z variable from z equal to 0 to z equal to 4 minus x square. That is from the base here to top of the particular column which ends at the surface of the cylinder. So the upper limit will be z equal to 4 minus x square, because it will vary depending on the x position of a particular column which has been chosen for integration with respect to z. Understood? And here we have to keep x and y fixed. Then we have to integrate the scalar function with respect to y variable from y equal to 0 to y equal to 2 in between this region, keeping x fixed. And at last the integration has to be done with respect to x variable from x equal to 0 to x equal to 2. So why is it so? Because the x equal to 2 point is that point where z equal to 4 minus x square plane meets z equal to 0 plane below along x axis. So this is z equal to 4 minus x square plane. So it is meeting at z equal to 0 along x axis, and that point is x equal to 2. Okay. Now, as we have all the limits for different variables, now we can use them for solving the volume integration. So first we will do the integration with respect to z variable. Then we get this form of the integration. And after that, sub integration have to be done with respect to x and y separately, like this. And putting the limits, we get this value. Okay. Next, let's discuss a problem where we will find the volume of a region common to the intersecting cylinders x square plus y square equal to a square and x square plus z square equal to a square, which is shown over here. Here the common region is actually this, in between two cylinders. Okay. And here the radius of the cylinder has been chosen 3 units to show how it looks like. Now you can visualize this in different way also. So here this is the region common to both the cylinders in first octet. Now the total region which is common to the intersecting cylinders will be 8 times of this region of first octet, right? There are 8 such regions if we include all the octants in 3 dimensions, right? So required volume will be 8 times of the volume of region of first octant. Right? Now, let's set different limits of variables of integration. So here z varies from z equal to 0 to z equal to root over a square minus x square, which is at this plane. Okay? And during integration with respect to z, we have to keep x and y fixed. Okay? Then we have to integrate with respect to y from y equal to 0 to y equal to root over a square minus x square, which is at this plane. Okay? And we have to keep x fixed. Then we have to integrate with respect to x variable from 0 to a, which is the radius of the cylinder along x axis. Right? Then putting the limits, we get this form of integrals. And here d tau is the elemental volume, which is this dx, dy, dz. Now we have to perform this integration. So for that, as you know, first we have to integrate with respect to z and we get this. Then with respect to y and finally with respect to x. And putting the limit, we get this value. Right? So today we have discussed solutions of various types of problems related to volume integrals. Right? And I believe that it has helped you a lot to understand how to perform volume integration. Right? So that's all for today's class. In the next class, I shall discuss about Gauss's divergence theorem, which is an important result for mathematics of physics and engineering. In particular, in electrostatics, magnetostatics, electromagnetic field theory, also in fluid dynamics. Okay. So, thank you for attending today's lecture. See you in the next class.